So I want to talk about a project, joint work with Vanya Chelsov, Maxim Fedorchuk, and Kento Fujita. So my goal in this talk will be to describe the component, which I'll just denote by M, of the K-moduli space of Fano threefolds and of anti-canonical degree 24 that's associated to even for short persons, you sometimes need to bring it up. That's associated to, so Fano threefolds in family 4-1 in the Mori-Mukai classification. These appear in quantum computing, so these are all the same thing. These are the pure states of 4 qubits and these are also just divisors of multi-degree 1111 in P1 cross P1 cross P1 cross P1. Okay, so let me state the main theorem, or the theorem that I want to state, which says that M is isomorphic to a weighted blow-up of the point, the smooth point, 2200 in a weighted projective space with weights 1, 3, 4, 6, with weights, so that's the weights of the blow-up, 1, 2, 3. Okay. So the way, so perhaps I'll just give the spoiler right away. This is just the GIT space of these hypersurfaces here for a suitable GIT. And this corresponds to a point which happens to be GIT polystable but not K polystable. So let me give some background and then get on to it. Is that legible for everyone? Yeah? Okay, thanks. Okay, so so yesterday Thibaut in his talk talked about Kähler-Einstein manifolds already, and so I guess the starting point here, or the background of this story, is this Calabi problem, which asks which compact complex manifolds have Kähler-Einstein metrics. So as I think Thibaut said yesterday, if you have a Kähler-Einstein metric, then you have to have a definite sign of the canonical class. And this was answered already in the 70s by Yao and Yao and Tian in the case of Calabi-Yau and general type varieties. But this became open until a lot more recently. This remained open until a lot more recently for Fano varieties. So this was what Thibaut mentioned yesterday, the Yau-Tian-Donaldson conjecture, now the Chen-Donaldson-Sun theorem. Maybe I should which was a characterization, which gives a characterization of Fano manifolds that are Kähler-Einstein. And this goes as follows. If X is a Fano manifold, then X is Kähler-Einstein if and only if X is K polystable. So there was So the original definition of K polystability, the original algebraic definition of K polystability due to Donaldson was in terms of these invariants associated to test configurations that Thibaut mentioned in his talk yesterday. So later in the talk, I want to give another description or an equivalent condition for K polystability, which is due to Fujita and Lee, which is a valuative interpretation of K polystability. So originally, and still I guess, Donaldson-Fataki invariance. And more recently, I think 2016, the Fujita-Lee valuative criterion, which I'll take as a definition of K polystability. Okay. So, but I guess, at least in my view, an additional, so these, the existence of a Kähler-Einstein metric is a really important and strong condition. It's like a canonical metric on your manifold. But recent results have I think, given another really important reason to study this notion of K polystability, and that's the results around moduli. So if you've studied a little bit Fano varieties, you know that in general they don't behave well in families, or there are some issues with how they behave in families, and it's actually really difficult to construct moduli for them which has good properties without any additional condition. Now, I think, or at least to me, it was a little miracle that K polystability allows you to form good moduli spaces. And these are the results of Xu and many collaborators, which are fairly recent, and which says that there is a projective good moduli space MNVK KPS, whose points parameterize Q Fano variety, K polystable Q Fano varieties of dimension n and volume V. So anti-canonical volume V. So in particular, the Yau-Tian-Donaldson or Chen-Donaldson-Sun theorem tells you that the C points of this moduli space correspond to Kähler-Einstein Fano manifold, Fano varieties of dimension n and volume V. Okay, so in dimension 2 and 3, so in any dimension, we know that we have that Fano varieties are bounded, that there is some structure on the number of families, but in dimension 2 and 3, we actually know a complete classification. So in small dimensions, we have a complete classification. And you could say, doesn't that tell us everything we need to know? Well, not quite, because this classification is birational. So it's in terms of, the morphisms that your variety, or the other projective spaces your variety maps to. So in the case of the classification of Del Pezzo surfaces, you know that I'm just talking about smooth here for the moment. You know that they are blow-ups of P2 or P1 cross P1 in so many different points in such configurations. That's what I mean. In dimension 3, for Picard rank 1, you're basically looking at images by projection from a line. In dimensions higher, the Mori-Mukai classification just classifies the extremal rays that can exist on your variety and how they interact with each other, and that gives you a complete classification. So, in dimension 3, so this is birational, not biregular. Doesn't really tell you when two such objects are isomorphic to each other. It doesn't tell you certain things. It's an amazing classification in other ways. Anyway, so for each of these families, so in dimension 3, you have 105 families, and you could ask, so for each family, you could ask, does there exist a K polystable member? So that's a version of the Calabi problem. And if the answer is yes, then this tells you that you have, so if yes, then there is a non-empty associated component of M3 minus K cube, if you like, for MNV of KPS. K polystable. So you have, if you have a K polystable member, then you have a non-empty associated component of this K moduli space that parameterizes K polystable degenerations of Fanos in that family. You know what the dimension of this is. So the dimension is the minus the Euler characteristic of XTX for any X in the family. That's just deformation theory. Fanos, smooth Fanos have an obstructed deformation. And if yes, you can then ask, can you describe this component completely? So in recent years, there's been quite a few works on on this. And this, yeah.
So you seem to claim that if there's one polystable member, then the whole Kuranishi family is in the...
So if there is one smooth K polystable member, you can actually show that the general element is K polystable or K semi-stable, and therefore, yeah. So the way very often, so for example, there's this book that several the authors are in the audience on the Calabi problem for Fano threefolds, and in most cases what you try and do is you try and find a very symmetric Fano in your family for which you could prove that it is K polystable, and then you deduce that the general element is K polystable, and then that does indeed tell you something about the Kuranishi family.
Sorry, so K polystability is an open condition?
K semistability is an open condition. K polystability is constructible. I'm sorry, I'm being a little bit imprecise in places about the difference between poly semistability, but yes, semistability is open. Right, any other questions? No? Okay, so let me talk about the family that I want to discuss. So the Mori-Mukai family for one, and I'll try and set up the, yes. So here, as I said, the smooth element of the family is a hypersurface of multi-degree 111 in P1 times P1 times P1 times P1. So it is given by an equation with monomials if I label coordinates there 1, 2, 3, 4. This is an equation with involving the monomials xi, x1 to the power I, y1, 1 minus I, x2, j, y2, 1 minus j, x3, k, y3 minus 1 minus k, x4, l, y4, 1 minus l, where ij, k, and l are 0 or 1. Right. Okay, so it's a combination of these monomials, and for the point of view of GIT, of course, on P1 times P1 times P1 times P1, you have an action of this group gamma 0, which is just SL2C to the 4, which acts on the P1s. And am I forgetting to say anything? Okay, so let me tell you a little bit about the birational geometry of this animal, which is very natural. So here, essentially, the birational geometry of X is going to follow the birational geometry, if you want to call it that way, of P1 to the 4. So here, let me just write down the projection to one of the factors. And then I've got the projection to the 3 remaining factors. And you can just take ijkl to be any permutation of 1, 2, 3, 4. So here, let me say that I do have 1, 2, 3, 4, just for the sake of notation. So here I can write the equation of x in the form x1 times some f plus y1 times some g equals 0. So this gives me here, when I look at the projection on to the first P1, so to x1, y1, so f and g are sections of P1 times P1 times P1 O111, also known as Del Pezzo surfaces of degree 6. So, so this gives you a dp6 fibration, or maybe rather a fibration with Del Pezzo 6 fibers. The reason I don't want to use dp6 fibration is that this is not an extremal contraction. Okay, so let me say it, not extremal. And if I just look at the base locus of this Del Pezzo 6 fibration, I'm looking at this intersection and this P1 times P1 times P1. This is an elliptic curve intersection of two Del Pezzo 6 surfaces, which I want to call C. And this map here is just actually the blow up of P1 times P1 times P1 along C. So PR234 is the blow up and this one is extremal. This is an extremal contraction. Yeah. So if I call E the exceptional divisor here, what you find is that E is just C times P1 in the smooth case. And I want to say that E on X is in the linear system minus 1, 1, 1, 1. We also have, let me call Y the fiber, Y a fiber or a general fiber of PR1. And then Y is in the linear system OX of 0. Sorry. 1, 0, 0, 0. So this is just given by, for example, x1 equals 0. Okay, so here, perhaps what's remarkable about, what will be handy later about this picture is that the pseudo-effective cone of X is just spanned by those divisors, EI, so from I equals 1 to 4, and so essentially everything you need to know about the divisors on this variety is really given by these projections to one of the factors or to 3 of the factors. Okay, and what I said before, the Kleinman-Mori cone here is generated or has extreme arrays corresponding to these PR JKL. Okay, so here this was, and maybe I'll say it now rather than later, when X is singular, we also have that the singularities of X is the intersection of these 4 divisors. Okay. So these smooth varieties were studied by Belousov and Loginov. I think it's in 2022, who proved that if X is smooth, then X is K-Pauli stable. And I'll come back to that proof a bit later. Okay, so that's all I wanted to say about the birational geometry. Let me say a few words about the GIT picture for this family. And here, essentially, we were quite lucky that this had been studied extensively by people in quantum computing. It seems to be the highest dimension. So there's a similar picture for n qubits, which are hypersurfaces of multi-degree 111 in a product of projective spaces, P1, in a product of P1s. You can describe 2 qubits, 3 qubits, 4 qubits, and then at 5 qubits, life becomes hard. So we were quite lucky, and here, I suppose, let me state the results. So I want to call V this space of sections of P1 to the 4 and O111. So the space of pure states of 4 qubits. So this one is 16-dimensional. So when we take the projectivization, we'll have a P15. And then I'm going to call for any F in there. XF will be F equals 0 in the product of P1s. And what these, I suppose the really important starting point is that these people, so the names are Verstraete, De Haan. You'll have to excuse me, my poor pronunciation here. So De Moor and Verschelde, and then Sterntal Djokovic, show that up to gamma 0 action, we can put F in normal form. So there are 9 families of normal forms. And the one that we are interested in is this one. So here I've just written a sublinear space of this V. So this is the span of these forms, which I've written omega 1, omega 2, omega 3, omega 4. And what these quantum computing people proved was that up to gamma 0 action, or rather, if your XF is smooth, then your equation can be taken in this. Sorry, I'm making a mess of this board. I'm not a natural, but okay. So okay. So if XF is smooth, so that's still the result. If XF is smooth, then the gamma 0 orbit of F intersects. So gamma 0, if you remember, was, I think I've conveniently deleted it. It's just the product of SL2s, of 4 SL2s. So intersects G. So you can find an equation which is in this space for your variety. And if you look at this space, then the forms that span it are really very symmetric. Okay. So you can put, so we can assume, I'm sorry for the slightly Baroque looking equation that's coming, but it's the right way of, I still haven't managed to let go of these things. So we can assume F is, has an equation of the form A plus D over 2 times omega 1 plus A minus D over 2 times omega 2 plus B plus C over 2 times omega 3 plus B minus C over 2 times omega 4 equals 0. And so these A, B, C, and D are, you know, if you like, coefficients of these, and they really are your parameters in G. Okay? So, okay. So, the theorem is that, so a group that happens to be used a lot in quantum computing is not just gamma 0, but it's when you take the semi-direct product of gamma 0 with the action of permuting the P1 factors. So they call it something like, I don't remember, SLOOC, and it has a meaning. Okay, so I think, so you can also ask what the action of this gamma on V is. And what you find is that if F is in V and XF is smooth, then actually the gamma orbit of F intersects this sublinear system G, or this subspace G. You can also find that if you have two two such representations. So if xf and xf prime are isomorphic as abstract varieties, then their orbits have to meet. xf is irreducible precisely when f is not in the gamma orbit of the point 0, 0, 0, 1. Maybe I should just write it right now. So this point 0, 0, 1 here in this, okay. So this is just the variety which is given by x1, x2 plus y1, y2 times x3, x4 plus y3, y4 equals 0. So that's essentially 2 quadrics. So this is a reducible. And then you can permute like the factors however much you want and so on. Okay, so if you are not in the orbit of that point, I think really what I should say is, yeah, okay. So these are the A, B, C, and D here that I view as a point of the projectivization of G. I'm not sure I'm being very clear here. Okay, and in this case, we can also say that if X is irreducible, then essentially your Neff cone of XF is inherited from the Neff cone of P1 to the 4, so that you have a fairly easy description. And then the important thing for the proof of K polystability is that if F is in G, so if you have an equation in here, then you know that the automorphism group of XF is going to contain a subgroup G, which is isomorphic to a z mod 2z to the power 4, which is generated by the restriction to x of this involution on P1 to the 4. So tau 1 is the involution that swaps, that exchanges the factors, the first 2 factors and the 2 loss factors. Tau 2 swaps the first and the fourth and the second and the third. And then tau 3 and tau 4 are going to act on each of the factors by involutions simultaneously. So tau 3 is the involution which for every I sends xi, yi to yi xi. So that's the involution of P1 that fixes the points 1, 1 and 1 minus 1. And tau 4 is the involution, is an involution that sends xi, yi to xi minus yi. So fixing the 0 and infinity points. So I should say that at the start of this project, this was one of the motivation to study this family, and
What's I star? What's I star?
sorry, the inclusion of X in the product of P1s. Sorry, so basically the NEF divisors on XF are just the restriction of NEF divisors on the product of P1s. So this means that essentially your NEF cone is just generated by these pullbacks of O1 on each factors. So it has a very very simple description. Any other questions?
So, in the singular cases, what about Q factoriality? I mean, does the rank of the class jump?
Good question. So in this, what about, does the rank of the class group jump? So not in the isolated singularities. Does it jump in the case of the curve of singularities? I think you could go to defect 2. Does it jump in the case isolated? I thought it jumped in the case... Yes, I think...
In the case of two singular poles, can be constructed, you
Yeah.
draw space of 4 lines.
Yeah. P3 and
and
4.
you contract 2 lines which intersect. So one group will be fine.
Yes, it's defect 2, right? Yeah, that's... You'll see further evidence of this jump in a second, because some of the K polystable degenerations are not even in a product of P1s, or some, and they're not in a product of P1s, which means the extremal rays don't go to the boundary, and so you expect that there's, if there was Q factoriality, you'd expect they would get. Okay. Okay, so here we have a description of the stabilizers G, and you also have, so maybe I'll just say that very briefly. So the theorem that we get to is that the GIT moduli space, or here the GIT quotient description is so perhaps I should say it in words. So we get this description here. And the meaning of this statement is that essentially the gamma orbit of PG, of this sublinear space G, covers all the GIT polystable points. And we understand essentially the stabilizer of G in gamma, sorry, which is the Weil group F4. And so we have a description, and we have an explicit map from this P3 here with coordinates A, B, C, D in this notation to this weighted projective space 1, 3, 4, 6. We know its degree. We know quite a lot of things about it. This also gives us, so let me call this is going to be my bold P. This also gives us a description. So this P here is M bar GIT, or NGIT. And we have a description of the boundary points here. So the boundary of this P is stratified. So we have a stratification which is given by, first of all, the points that correspond to a reducible element, which is basically this 2, 2, 0, 0 here, this product of quadrics in different factors. So we have essentially a product of the quadric in the first two factors, P1 times P1, multiplied by a quadric in the second factor. Then we have a locus where we have a curve of singularities, an A1 singularity along a curve of multi-degree 1, 1, 1, 1. Then we have a locus where we have two A1 singularities, so 2 isolated nodes, 4 isolated nodes, 6 isolated nodes. So this is quite, and you can give a description of each of these. So for example, here we have only this point 2, 2, 0, 0. The pre-image in this P3 is 12 different points, and so on. So I'm not, so I should say, yeah. And perhaps the last thing I should say is that this one contains in particular the toric-Fano threefold, which is just given by x1, x2, x3, x4 plus y1, y2, y3, y4 equals 0. This is toric-Fano with ID 12645. Is that the one? I think reflexive ID 12645 in the graded rings database. And so this was known to be K polystable. Okay, so perhaps the theorem here is that, or that I want to discuss here briefly, is that for every P except this P red point, the associated Fano, so that includes all the GIT polystable degenerations, is K polystable. Okay, and so what I had hoped to do in this talk was perhaps discuss an example of proof which illustrates the use of these valuative criteria and the Abanzwang estimates.
Can I make a comment? The fact is that this V is a theta representation. What you just erased is a Cartan subspace, and everything you spin is an instance, a nice instance of this V vector.
Fabulous. Thanks. Can I ask you about that after, though, because... Okay, so the methods I wanted to explain a little bit are this. So let me do as an example the case when the singularity locus of XP is isolated. Okay, so the valuative criterion of Fujita-Lee tells you that replaces the study of Donaldson-Futaki invariant on test configurations by the study of an invariant of valuations over X. So in order to state it, I want to introduce E over X to be a prime divisor over X. So this is a divisor that lives on a model Y, proper normal over X, and we say that the beta invariant of E is the log discrepancy of E minus, I don't know, how do people call that? The action of E. And so here, this log discrepancy is just 1 plus the order of the relative canonical along E. And this S of E you can think of it as a sort of average volume of divisors on the line between minus ky and minus kx, I suppose. So S of E is one over minus k to the n. So this is a normalization of 0 to infinity of the volume of, so I had here F. F upper star of minus kx minus t dt. Okay. So at some point, this divisor hits the boundary of the pseudo-effective cone. This volume becomes 0. You can think of this divisor as basically tracing the line between minus kx or the pullback of minus kx and minus ky. And so you're taking an average of the volume along that line. Okay, so the Fujita-Lee criteria states that X is K stable or K semi-stable if and only if beta of E is strictly positive or greater or equal than 0 for every divisor E over X. So I'm already over time, so perhaps I will just mention that the crucial point here is that, so you'll tell me you've replaced something involving all possible test configurations by something involving all possible valuations. That's not necessarily much simpler. But there is, both for test configurations and for this criterion, an equivariant version due to Datta, Zeklehidi, and someone else, and Liu in the more analytic formulation, and Zhu and Zhuang in this formulation, which says that if the automorphism of X is reductive and beta of E is positive for every G invariant, for every auto X invariant, prime divisor over X, then X is K polystable. So essentially, you only need to check. You only need to check divisors that are invariant under subgroups of the automorphism group. So here we have this mu2 to the 4 subgroup, and there's not so many invariant loci. What is used in general, and I'm sure Elena will speak some more about this on Thursday, is these very powerful estimates due to Hamid and Ziquan Zhuang, which basically allow you to bound beta or an equivalent valuative invariant, which is the delta invariant, when you have a sort of flag of your variety. So here, I'll just say one more word about this case. For any, so here essentially you want to look at divisors which have an invariant center on X. There's no point that is an invariant center. So you look at possible curves or surfaces that have invariant centers. Then you look at their image on those projections to any of the factor P1. And because under the action of tau 3 and tau 4, there's no invariant point on those P1s, then you know that your center has to map surjectively over P1. So if you then take a general point, you can show that there is a smooth Delpezzo surface of degree 6 that goes through it, and then you can apply those Abend-Zhuang estimates. So here what I should say is that being able, so this is all very computable once you have a good understanding of the effective cone of your divisors, because these P's and N's are Zariski decompositions. So you have to have an explicit understanding. And yes, there is another story which is about replacing this point 2200, which can be built by hand. It's in our paper. And you can show that indeed this is the weighted blow up of this GIT moduli space. And then to finish, I should say that there is yet a completely other story that maybe some members of the audience know a lot more about, which is that these Fano varieties themselves are moduli spaces of vector bundles over some curves, parabolic vector bundles on curves, which is how we knew about the large automorphism group by suggestion of Carolina Araujo. So I'll stop here. I'm very sorry I went over.